Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. This particular lecture is essentially how the theory of vibrations as we learned through this course, how that can be used as an example in health monitoring of a typical mechanical equipment. So, the condition monitoring refers to monitoring the health status of various mechanical elements like bearings, gears, shafts and other elements which are critical to the operation of the machinery. So, we use mechanical vibration response in diagnosing whether the system is operating as per its design and is there any failure that is about to happen. We talk about the last topic of this course, that is condition monitoring. It's related to vibration theory as such, although the whole field of condition monitoring is quite wide and multidisciplinary. It's not only related to vibration, so it encompasses many fields of engineering as such. But here I am just going to give you a brief glimpse and correlate or relate it with vibration theory. Condition monitoring, also called as the health monitoring of assets, either they can be assets or they can be machineries or structures, civil structures. Their health is monitored or their condition is monitored by different methodologies, and any deviation from a healthy condition is detected by processing various parameters or various signals and then used for ensuring that the condition is always healthy and the untimely failures are avoided. So, in the context of mechanical vibrations, I am giving you an example of a grinding machine tool here, which is creating finely polished or finely machined surfaces on the workpiece using a grinding wheel, and then if the vibratory motion of this grinding wheel increases for a variety of reasons, then the workpiece which is going to be machined is going to be of reduced quality. So, the quality of the machined parts are going to be influenced by deteriorating condition of this system, which is actually a vibratory system. You can see that this wheel is nothing but a disc, and it is supported in different bearings, and this itself is now a typical vibratory system. So, if the health and or the condition of this vibratory system is not kept within the closed tolerance values, then the quality of the product is going to be influenced, right. The other example is of a defense equipment. Now, the defense equipment, like what you see here, has many mechanical parts. There are engines, there are transmissions, there are gearboxes, pumps, and so many critical machinery equipment inside, which if they deteriorate in their quality of operation, then the reliability of the mission being undertaken is will get compromised. So, from the reliable operation and the success of the mission, these vibratory system or these equipment acting like a vibratory system has to be kept in the working condition or the most effective operating condition. The third example that I am giving you is related to aerospace industry, where this helicopter with gearbox as one of the critical element, mechanical equipment, if that gearbox, which is part of a transmission system, if that fails, then there is a serious threat to the lives of the people. So if the condition of each of these equipments, which are more or less every time are acting or are actually vibratory systems, and their condition can be assessed using vibration as a parameter, is very important, very critical. So this is a domain within the vibration engineering, where we may use among other things vibration as a significant and important parameter for keeping the condition of these equipment up and running. So to the best of the possibilities. Now, what are these condition monitoring parameters which we can use for ensuring the machinery or the equipment works perfect? There are various parameters, like an oral parameter. For example, in an automotive engine, if you take your vehicle to the garage, the mechanic will immediately start it and look for some audio symptom, or the parameters like oral parameters, where he will listen to the sound coming from the engine to detect any anomaly in the system. Okay, so sound as one parameter. Sometimes some equipment have possibility of detecting damages using some simple visual observation, like using boroscopes in the heat exchanger or furnaces, where visual observation is good enough to maintain the condition. The other is the temperature. So if you take the bearings, the temperature of the bearings will tell you whether the condition is appropriate or it is deteriorating. Wear debris, either from the bearing oil or from the gearbox oil, if you drain out the oil and look for the particles, the debris particles, which can indicate whether the wear is abnormal in the gearbox or in the bearings, and that will tell us the health or the condition of the equipment. In addition, yes, vibration is one of the most convenient and important diagnostic parameter, where the health of the machinery is diagnosed based on the quality of vibration, and we will discuss about this parameter in more detail. But there are, of course, other parameters such as acoustic emission parameter, or operational variables such as the pressure, and then the the temperature of the equipment. Sometimes the speed, for example, in power stations, the vacuum in the condenser or the power being generated, as the operational variables are used for tracking the condition of the equipment, right. So these are just the glimpse of all various parameters which can be made use of in monitoring the health of the equipment. But vibration is the one which we are going to focus, because there is no dispute about vibration being the most convenient parameter to measure. It comes with a cost, but it is very effective. That's the reason. Now, all these parameters have different advantages and lacuna. So this particular figure shows that if the equipment is behaving well up to a certain operation, after that, because of a general wear and tear, or because of the failure of some subcomponents, the condition starts deteriorating or degrading, and you have this much period of time to ensure replacements or corrections. Otherwise there will be untimely failure of the equipment. Now, it is possible that by employing some of the parameters which we have seen in the previous slide, one can keep track of this deterioration. So among the total time or opportunity for the corrective action, if you rely on noise, it may be too late to figure out the damage. The noise starts emanating generally a little later in the progression of the damage, compared to other parameters such as visual inspection, temperature changes, and maybe lubricant analysis for the wear debris particle or a lubricant quality. But it has been observed that vibration is a parameter that gives you early warning symptom of any change in the condition of the equipment long before temperature shows up or long before the noise starts giving its indication. So therefore, in general it has been observed that this vibration as a parameter is an important one to track the condition of the equipment. Now let us focus on how this vibration is going to give me an idea about the degradation or a deterioration of the condition or health of the equipment. So I am just taking a simple example of an electric motor. You know that this electric motor is having rotor, and then the rotor is supported on these two bearings, and this rotor spins in the inside a stator winding under the and then these bearings basically support this spinning rotor. So as a vibratory system, this rotor can be treated like a spinning shaft supported on bearings, and this we know that a simplified way to represent this is in the form of a vibratory system. So a shaft plus a rotor, if the shaft is big enough in terms of its diameter and compared to its length, can be treated like a rigid one without any deflection, and the bearing stiffness can be treated as the spring element in the vibratory system. The damping in the bearings can be simulated here or assumed here as the dashpot element for our typical single degree of freedom vibratory system. The inherent unbalance in this entire rotor can be the excitation force to the vibratory system. So the force acting on the rotor is going to be the rotating unbalance in the shaft. Of course, in addition to that, there will be magnetic pull which is going to be generated because of the operation of it in the stator winding. But in general, we can treat the excitation force coming from the rotating unbalance. Now, if this is your vibratory system which has certain stiffness, mass and damping properties, I can write then the governing equation of motion for this vibratory system, as we have done many times now, mx double dot plus cx dot plus kx equal to f of t. Now, when things are going fine and if everything is working all right, the system is in the best of its health and condition, this equation is the equation that describes the dynamics of this particular system. Now, we would like to look at what will happen if the condition deteriorates, but before we do that, we know that if this f of t is the excitation coming from the rotating unbalance case, then the response is going to be given something like this. You already know that the response to a harmonic unbalanced excitation force is a pure harmonic signal as this, and the amplitude can be obtained from the parameters of the vibratory system as well as the excitation system properties like the unbalance. But this is going to look like a healthy condition vibration of the rotor, which I can measure by recording the vibration of the shaft which is coming out from there. But let us look at this system little more closely, and one of the most common element of this vibratory system which generates faults or deteriorates its condition is the bearings. So if I consider this one of the two bearings here and see this bearing, it is possible to see that this rotor is supported by the bearing which I am defining as the spring which I have used here. Okay. Now this bearing itself is going to have a very little or a very minor fluctuation in its value based on the ball position. So if the balls are located like this about the vertical gravity line, then there will be some stiffness based on the ball positions, right. all along the circumference. But if this ball comes to this central position and then the other balls are located like this, the stiffness of this bearing changes, and in effect, in short, the stiffness of the bearing is going to fluctuate based on the position of the orbiting balls, and that small fluctuation in the bearing stiffness is going to create excitation to the vibratory system. And how is that going to happen? Because we all the time assume that the bearing stiffness is constant, but I can use this what is known as a varying compliance effect of the bearing, that there is some mean stiffness value, as you can see that there will be some mean stiffness value, but there will be some very little perturbation or variation in the fluctuation in the stiffness value. So there will be some delta k, and some it might fluctuate with certain frequency omega f, right? And this is how, instead of constant k, I am going to have a varying stiffness, and that equal to f of t. So even if there was no excitation except the gravity, the governing equation of motion will have this additional excitation term, which is going to create an excitation to the vibratory system, and that is going to create a slight amount of vibrations to the bearing. Now this fluctuating part is very little, and so it is generally not going to create major condition deterioration, particularly when the shafts are long enough and flexible. Anyway, but that is not the point. What basically is being seen here is that even for the healthy conditions, this particular parameter of the vibratory system would be not a constant value, but will be having some fluctuating element that is going to create certain kind of vibrations. But in addition to that, if the bearing raceway generates a flaw or a defect on its raceway, like what you are seeing here, and that is going to create a problem for us. How is that going to happen? Each ball will pass through that defect, which can happen because of poor lubrication, excessive loading, and so many conditions and parameters are responsible for that. If that localized defect is generated because of its operation, that localized defect will cause sudden excitation to the rolling ball as the ball passes through that defect, and that condition can be considered or can be assumed to be like this, where each crossing of the ball or each passage of the ball through this localized defect is going to generate impulsive loading on this particular inner race of the bearing. Okay, so as this ball hits here, then the next ball will hit, then the next ball will hit, and this is how periodically you will have excitation force generated on the inner race, which actually means that the force in this particular governing equation of motion is going to be modified, because this f of t is not only going to be this, but a sudden impulsive excitation force because of the interaction of the rolling ball over the defect is going to create an impulsive loading on the bearing inner race, and inner race is nothing but fixed on the shafts. The shaft is going to vibrate because of such kind of a excitation. So what is going to happen because of this? The response is going to be impulsive for a short period of time when this particular impulse or this particular impulse acts. So each of these impulses are corresponding to each of the passage of the ball through the localized defect, and therefore in general the response could have been a harmonic response because of the rotational unbalance, but now that gets modified in the form of an impulsive high frequency vibration response, right? And because the geometry of the bearing is such that the time gap between successive balls hitting this particular local defect is related to the geometry of the bearing. So this repetition period after which these impulses are generated, that can be obtained from the geometry of the bearing, and it's called as the characteristic defect frequency. So by looking at the time domain data from the measured vibration signal, one can easily identify whether the bearing is healthy or not healthy. The point here is, you still have the same basic vibratory system being modeled, and some parameters of this vibratory system, mostly the stiffness or the excitation function, will get altered by the presence of many of the mechanical defects which typically appear. Okay, so this is just one example of a rotor bearing system as a vibratory system, and how condition deterioration in one of these elements of this vibratory system generates different kind of a vibratory response, and by detecting the differences in the response, one can identify if there is any fault and what type of a fault it is. The other example is that of a gearbox or a geared rotors. You know that the gears are basically teethed elements engaging with each other and transmitting the torque and power. So if you consider one such pair of gear teeth, they are going to engage all along from the tip of the gear tooth to the root of the gear tooth, and so it so happens that depending upon where the teeth are in engagement, depending upon whether the engagement is taking place at the tip of the tooth or at the root of the tooth, the stiffness is going to be different. It is very simple, because if you consider the tooth to be a cantilever, if you apply the force here, the corresponding displacement is going to be larger, but if you apply the same force, contact force, here at the closer to the root of the tooth, the displacement is going to be much smaller as compared to when the same force was acting here at the tip of the cantilever. So it basically, this force to deflection relationship generates the stiffness, which is not going to be a constant value based on the engagement of the tooth at different locations all along the contact profile or that length on the flank. This effective stiffness of the tooth is going to be different in each instant of time during the entire contact cycle. So basically, you may then consider this contact to be in the form of a stiffness and damping. Damping will come because of there is always a sliding action between the two teeth, we already know from the kinematics, and that friction, if the lubricant is not there, there will be a Coulomb friction damping. If the lubricant is there, then there will be some viscous damping due to the sliding motion, except at the pitch point. Now, so the point is, because the stiffness of the tooth is different at different times, but still that stiffness can be modeled like a gear mesh stiffness kg here, and then I can write the governing equation of motion of this particular geared rotor system. Now, of course, this is going to be in theta terms, but I am just giving a representative equation, and the most important part in this particular case is that the contact point, since it is sliding from the tip to the root and back again, this stiffness is not going to be a constant stiffness which we typically use for our general linear vibratory system. Okay, the k is not going to be a constant, it is going to be a function of theta or time, and quite similar to the bearing case that the stiffness was not constant. It can be shown, this is definitely not the point of discussion, but you can find out from literature that during one contact segment, that means when one pair of teeth starts engagement until the contact cycle completes, one contact cycle gets completed, if the contact ratio is more than 1, the stiffness of the gear teeth that changes in this way, one cycle. Okay, so stiffness when one pair of teeth are in engagement, this is the gear mesh stiffness. If two pairs of teeth are in engagement, this becomes the stiffness of the gear, right. So The point here is that k is not a constant value, but that k is going to be dependent on time or angle of rotation, because at one point of time the stiffness is so much, suddenly it drops, and then it follows this cycle, which actually means that the stiffness is a continuous function of time. Okay, and because of that, as we discussed in the previous case as well, that this k is not going to be you can treat this k to be a constant term, mean value, and some fluctuating component, that is going to be kt, which is going to be fluctuating component. So if I keep the mx double dot plus cx dot plus this constant part on the left hand side, then the right hand side is going to be this kt into x, which is basically arising out of the fluctuating or a varying varying part of the parameter k, and that is why this system is called as the parametrically excited system. This excitation function kt into x actually becomes now the excitation source. So even if there is no unbalance, even if there is no other external excitation, the system will get excited and will generate vibratory response. Now this is something which is happening even without any deterioration in the condition of the system. That means even if the gears are perfectly healthy, this kind of excitation is going to be there. But if the gear generates a flaw like what you see here, a spall on the flank, there will be some distortion in the stiffness profile. So the stiffness profile will slightly change, and that change is going to get reflected in the changed vibration response, which is what we are going to show you. So one can again use this particular gearbox as a vibratory system. So I can model the shaft, the disc, the gear, one shaft and the second shaft as a simple vibratory model, and the connection between these two gears will be through a gear mesh stiffness, which is k, which I can simulate as a function of time based on this known stiffness variation profile. And I can also take the bearing stiffnesses and damping into account, and I can make a multi degree of freedom vibratory model from this system and generate the response. If a gear having 27 teeth has a fatigue crack on one of the teeth, if suppose there is a crack in the teeth, then that crack can generate a dip in the stiffness value, overall mean stiffness value. That stiffness is going to reduce because the crack is going to make the tooth weaker. And so if only even one teeth is having a crack or any flaw, the mean stiffness level drops at that particular engagement cycle of the first teeth, and then the rest of the teeth are perfectly healthy, and therefore they generate the kind of stiffness variation that we discussed earlier. Now if you use this, the time domain response of this particular gear teeth pair is shown here. So what you see is that time versus amplitude response, and you can notice that whenever such a defective tooth comes into engagement, the vibration at that particular point gets changed from a normal healthy condition. So these are the healthy teeth vibration response, and these are the defective teeth vibration response. So rest of the times the signal is more or less stable, but whenever such a defective tooth engages, there is a localized change or a transient response change that is observed in the response history. Now if you take the Fourier spectrum of this particular time domain data, you get the frequency domain signal, something like that. Now you don't worry too much about how to get that FFT. Some of you might be already aware of how to get the frequency spectrum from the time domain data, but the point is these periodic perturbations or signal changes that happens because of the defective teeth generates a peculiar vibration response pattern which is observed in this frequency spectrum. If the defect is not there in the teeth, then the general vibration signal would look like these frequencies only, and ideally this is how the spectrum will look like. But because of uh, the defect in some of the teeth, you can see that these kind of sideband vibration frequencies will appear, which can be used for diagnosing the health of the gear. Now the whole purpose of telling you all of this is not to teach you details of the health or the diagnostics or the dynamics of the geared rotor, but to show you a glimpse of how vibration as a signal feature can help you diagnose the deteriorating condition of a vibratory system like a gearbox. This in no way is going to demonstrate or discuss in detail the dynamics of the vibratory system of a gearbox, but only to show you how vibration, which we learned through the theory elements, elementary theory of vibration, can be extended to study the dynamics of complex mechanical vibratory systems, and that can be used for diagnosing the health of the mechanical equipment. The other example that I would like to finally give you is a fatigue crack. So a fatigue crack can appear on the shaft like what you see here, due to a large fluctuating stresses, bending stresses in the shafts, because of the flexible shafts being used with high speeds and higher loads, and under the against the aggressive environment like high temperature conditions, and that creates a fatigue crack. So this is a picture of the actual fatigue crack that has been generated in a shaft. So you can see a fractured surface here, and this is the crack front, and this is the crack area, right? So when such kind of a fatigue crack exists, what actually happens is that at this particular cross section of the shaft, only this area is bearing the load. That means this particular part of the total cross sectional area, this area does not contribute to the stiffness or load bearing part of the cross section, right? So only this area of the cross section bears the load, and therefore the stiffness in this localized cross section reduces significantly, and that creates a change in the stiffness value. So here, if you consider this to be a horizontal shaft under the gravity loading, and this kind of a crack exists in the cross section, as you can see exaggerated view of that crack, which will open the two areas and will create an open area here, which actually means that only this area of the shaft is bearing the load. Okay, so the crack is wide open. Now this crack, if it is assumed to be on the underside, because of the tensile forces on the underside or on the lower side of the shaft, they will open the crack here. But when this crack, when this shaft rotates by 180 degrees, the same crack will go at the top, but because of the compressive loading on the top side of the shaft, when the crack goes at the top side, it will get closed because of the compressive loading that appears on the top side. Okay, so this is something which is shown here. So at theta equal to 180 degrees, this is theta equal to 180 degrees, that is on the on the lower side, this crack is going to be completely open. Okay, but the same crack, or when the shaft rotates by 180 degrees, when it goes at the top side, the compressive loading on the cross section will close the crack and the entire surface will bear the load. So this is shown here at theta equal to 0, when the rotor is, or the crack is on the top side here, this cross section is completely closed, the crack closes, but here this is completely compressive region, so the crack is half closed, right, and then it is half open here. This is at theta equal to 90 degrees. If you consider this to be 180 degrees, and so the rotor is always rotating in this direction, and then after every 90 degree of rotation, the crack area will continuously open and close. So at 180 degrees of position, where the crack is on the underside meaning that it is here, the crack completely opens, and now with the further rotation, again half the crack, which is going to be under the compressive region, and this one is in the tensile region, the half the part of the crack is going to be closed, and then here it is going to be completely closed. Now if you use this to show how the stiffness of the shaft changes as the crack changes its orientation as the shaft rotates, you can say that at theta equal to 0 degree, the crack is completely closed, and it is like a uncracked rotor stiffness, which means that the crack is almost the effect of the crack on the stiffness is not there at all. Okay, so if the crack is half open and half closed, the stiffness drops to a certain value, and when it is completely open, when the crack is completely open under the action of the tensile loading, the stiffness drops to a significantly low level. Okay, and as it rotates further, half open half closed, it will have certain stiffness value, and then again back to a completely closed condition, the stiffness is again back to the same as the uncracked shaft. The point is, had the rotor been without any crack, it's an intact rotor, the stiffness does not change at all. Okay, so it remains constant irrespective of the rotational position of the shaft. Obviously you can agree with that, that if the shaft is uncracked, it is going to have the same stiffness all through as it rotates, so the stiffness does not change. But because of the crack being opening and closing continuously and gradually during a rotation, the stiffness of the shaft fluctuates like this, which again brings me back to our governing equation of motion. We have always been solving this governing equation with mx double dot plus cx dot plus kx equal to f of t, but this is the case where a damage or a fault in the system in the form of a fatigue crack, it's a fault, it's a flaw. That fatigue crack changes the parameter of the vibratory system, in this case the stiffness. So the stiffness is now going to be function of theta, the angle turned by the rotor, and therefore it will generate excitation to the vibratory system exactly the way we have discussed in the previous couple of slides, that parametrical variation or the variation in the parameter of the vibratory system as a function of time is going to create additional excitation to the system, and that is going to create a specific response feature. So for example, if I had considered an uncracked shaft, a rotor without a crack, the response under the action of unbalanced excitation force is going to be harmonic. Okay, but this kind of a stiffness variation which you see here, if I use this in the equation of motion here, then I will get a response which is going to be seen that way. Okay, so I am showing you the response of a typical response of a cracked rotor, right. So this is the response as a function of time. So instead of a harmonic signal, you will see a periodic signal being generated, and that is all because of the varying stiffness value which is shown by this particular variation. And if I take the spectrum of this or a frequency decomposition of this, you can see that there are multiple frequencies that appear, harmonics of the rotational frequency in the spectrum, and had it been an uncracked shaft, a benign a healthy shaft, it would only show under the action of unbalance only the first harmonic or the rotational frequency in the response or the spectrum, whereas these additional frequencies, presence of these additional frequencies theoretically can indicate the presence of a fatigue crack in the rotor. Now again, this is all to show you how every mechanical vibratory system is defined or characterized by a governing equation, and majority of the mechanical faults somehow either modify the forcing function or the parameters of the vibratory system like stiffness or damping, but 90+% of the times it is the stiffness which gets modified, and that modified stiffness generates a slightly different kind of a response, vibratory response. And when you compare the original healthy condition response with the changed vibration response, then the difference basically will tell you what could be the reason. The first thing is, it establishes that there is a deterioration in the condition of the equipment, and then by analyzing that signal through variety of means, one can identify the possible fault in the system, right. But most of the mechanical systems, when they are when they undergo some deterioration in their condition, they will they will give rise to a specific vibratory response which is characterized by certain parameters, and using those parameters one can diagnose the condition of the equipment, right. But at the heart of it, it again is the basic vibration theory at work. So just to wrap up this part, there are of course n number of different kinds of faults in mechanical vibratory system. We simply cannot get into the details of each one of them, and this particular topic has been just taken to highlight as one possible application area of vibration theory. So if there is an increased unbalance, we know that the first harmonic or the rotational frequency related response increases. If you have a misalignment, higher harmonics will appear because of the misalignment in the shaft, in the coupled shafts. If there is a bearing wear, the response again would change by in the form of a changed orbit plot. Rolling element bearing we have already discussed. We have discussed how the gear tooth damage will cause a different kind of a vibration response. And if there is the rotor, when it is rotating and if it is surrounded by a stator, if it hits and strikes the stationary rotor, there is going to be a peculiar vibration pattern which will get generated, and all of these are going to generate specific vibration symptoms which if properly analyzed can definitely point to a certain flaw, which is why this particular field is exciting and extremely dynamic. It is multidisciplinary and a lot of research is still going on in increasing the robustness of the diagnostics, okay, of the condition. Finally, I would end with one of the example of how industry on the shop floor can use the severity chart for assessing the preliminary condition of the mechanical equipment. So what you see here is a gearbox from where sensors can be placed at an appropriate location, and that sensor can generate vibration signal. That sensor vibratory signal, let's say x or x double dot, is plotted against time here. This is a typical vibration response signal which I can get from a gearbox, and I can get an RMS value of this gear vibration signal. The theoretical expression for the root mean square value obtained from a time domain data is shown here. Of course, this is this shows that x as a continuous function of time, but you can use a discrete discrete values of x at every sample value, and then instead of integration you can sum all these values and find out the RMS value of that digitized signal. But you can also find out this RMS using this expression. Once the root mean square value of the vibration signal recorded on the equipment is obtained, then using the ISO standard one can categorize the equipment whether it is operating with healthy condition or not. Okay, so depending upon what is the capacity of the equipment, the capacity of the machine, there are prescribed values of the vibration velocity, RMS value of the vibration velocity. So for example, if we are taking the vibrations on a 15 kilowatt machine, um, and the vibration RMS value turns out to be 1 millimeter per second RMS, which means that I am, and that if the foundation is rigid, I am basically located here, because 1 millimeter per second RMS vibration velocity means that the condition is almost like a new machine, and the machine is perfectly healthy and I do not need to worry about it. But if it reaches to maybe more than 2.5 millimeter per second RMS value, velocity value, then there could be a little bit of a concern that it is going into a region where it is not absolutely healthy, and I need to take care of it. If it continues to grow from that point onwards, then some corrective action has to be taken. And of course, if the vibration velocity value goes beyond 7 or so, which actually means that I am getting into a dangerous kind of operating condition. So this is in nutshell as a broad guideline chart that you can find out whether your machine condition is healthy or not, based on the measured vibration value, and using that vibration value I can find out from this chart whether the system is in a healthy condition or not. Okay, so this is in general the way the vibration based condition monitoring used to have been carried out in the industry. Okay, but of course now people have migrated to more sophisticated approaches, and much more involved diagnostics is carried out instead of only based on the RMS value, but this is the basic of the vibration based condition monitoring. So the summary of this lecture, we discussed how various physical parameters are possible to monitor the health of machines, and of these various parameters the vibration has been considered to be one of the most promising parameter to monitor the health, and we deliberated as to how different machine elements such as bearings, shafts and gears, they produce vibrations which are very peculiar to the defect that they have, and so the vibration response change can be directly correlated to a fault brewing up in the system. And that is what we discuss, the faults as a source of change in vibration, and a careful deciphering of the changes in the vibration signature can act as a diagnostic approach. The review questions based on today's lecture. These are the answers. So here we are at the concluding part of this course, elements of mechanical vibrations. During last 12 weeks or so, we had a sufficient in-depth understanding of the fundamentals of vibration, and what we are going to do here is to take a very brief recap of all what we learned in this course. So we started first with a simple single degree of freedom system model of a given vibratory system. So we limited ourselves to just a single degree of freedom for a given physical system. We explored as to how the governing equations of motion is obtained, how the natural frequency is calculated, and in addition to that, we also understood how the response to initial conditions is obtained, and in that context we considered a couple of interesting examples to drive home the point. And once the basics of the single degree of freedom system in case of undamped free vibration has been explored, we then looked at how the damping plays its part in attenuating the vibration amplitude over a period of time. So in that context, we considered a couple of practical damping sources, for example, a viscous dashpot, which is typically used in automotive systems, and in a steam turbine case of a Coulomb damping, how it plays its part in attenuating the vibration response. Once different damping models were considered, we then shifted our attention to response to arbitrary excitation, wherein we understood how a short duration, arbitrary or transient excitation can be accounted for in finding out the subsequent vibratory response. So in most of the times we considered this vehicle as one of our physical vibratory system, and then simplified it as per our convenience, either as a single or a multi degree of freedom system. So after having discussed the free vibration response both in the case of no damping or with viscous damping case, we then shifted our attention to the case of forced vibration, and in that we investigated the harmonic excitation as the primary source of excitation for a practical vibratory system. We extended this understanding to investigate how the response to periodic excitation can be obtained. And then we also explored the concept of transmissibility, both displacement and force transmissibility, and understood the relevance of tuning various parameters so as to derive the best transmissibility condition, indicating that the transmitted force or the transmitted displacement to the target is minimized. So having explored the single degree of freedom system and its response character for variety of operating excitation sources, we then shifted our attention to a 2 degree of freedom system. And in this context, we found how the same vibratory system, now if we want to capture some of the dynamics that we miss out while considering only a single degree of freedom system, can be obtained. And therefore a suitable governing equations of motion for a 2 degree of freedom system were formulated. The concept of mode shapes was introduced, and this was followed by the concept of vibration absorbers. And in that case, we took couple of practical examples of how these vibration absorbers are used in practice, either in the civil structure or in the mechanical automotive systems. So having considered a 2 degree of freedom system, the concept of mode shapes and other aspects of 2 degree of freedom system, we started exploring how a multi-degree of freedom system can be modeled as a set of governing equations of motion which are typically coupled. We understood how a system with many degrees of freedom can be modeled as a vibratory system. In that context, we also explored how the numerical methods can help us model the similar systems with much more accuracy as compared to a lump parameter model. So in this case, an example of a Holzer's method or a Mikkelstadt problem method of finding out the natural frequencies and mode shapes of a typical complex structure was discussed. So in an example of a music box cantilever beam, it is almost indispensable for us to use numerical methods rather than lumping the parameters. Then this was followed by continuous systems, wherein we considered the entire system or a continua as distributed parameter system, wherein the mass and stiffness properties were a continuous function of the spatial variable. And in this case, we considered the example of stretch strings, vibrations of a bar, and that of the beam, and essentially then understood how the differential equations of motion for such continuous systems are characteristically different compared to the lump parameter model. And the last topic was condition monitoring, wherein we have discussed how the presence of typical mechanical faults in a vibratory system changes the vibration behavior and the response character of the vibratory system. And based on the differences in the healthy condition and in the defective condition, the change in the vibration behavior can be related to the type of fault and the severity of the fault. So essentially, vibration as a phenomena has been discussed in its elemental level, and in a short course of just 12 weeks it is difficult to do justice for all the aspects of the vibration phenomena. However, fundamental theory of vibration has been presented, and I hope by following these lectures you will be in much better position to understand some of the main and important concept of this wonderful field. And I must thank you all for joining this course, and I look forward to interacting with you in future again.